really stuck. So this is a relative amount. It's not measured. So basically, they assigned, because fluorine's got the strongest pull, they assigned it a value of 4, and then everything else is lower than that based on how strong the pull is. So it is a relative amount that describes the pull on a pair of bonding electrons. So what did you notice about electronegativity values from the graph? Value of 0. Why?
Because they're unstable, they don't need to.
Yeah, they have full valence shells. Therefore, don't bond. So they've got no desire to pull somebody else's electrons because they've got a full set, so they're quite content. We can actually, it turns out we can actually make some compounds with the larger noble gases because there's so much space around them. They have been made in the lab. Okay. Who has then the largest values? Where do you find them? The largest values. Electronegativities. Halogens, do you agree? Largest electronegativity values. Group 1? No, they're not the largest. Okay, if you were going to make a comparison between metals and non-metals, who's got the larger values? Non-metals do. What do non-metals want to do?
They want to take.
Yeah, they basically want to take electrons. So, non-metals values are higher. Especially the halogens. Especially the halogens. And this is because their size. Because they're so small, they have greater control over neighboring electrons. Okay, so the smaller you are, the more effect your positive nucleus can have on electrons around it. So the smaller values goes to the metals because they are larger. Their positive pull is less felt. Okay, so that's really all we need to know right now for electronegativity, yeah?
When you say the small one, because there's less of a distance between their nucleus and the other.
Yeah, yeah. The smaller you are, the closer the neighboring atom can come into your nucleus. All right. Are we ready? IE, ionization energy. So this is the energy required to remove an electron. So if X is some element, it's the energy that you need to pull off an electron from the atom. So you form an ion. An atom. The smaller atoms hold electrons more tightly to the nucleus. Therefore, it's harder to pull them off or to pull them away. So the smaller atoms hold electrons more tightly to the nucleus. It's harder to pull them away.
Therefore, meaning that electrons are further away from the nucleus, which means that, in turn, means that the pull is less.
Yeah. Takes less energy because it's a bigger atom, so that electron is held less tightly. So we say that cesium is more metallic than sodium because metals react to give up an electron. So on the periodic table, the elements on the left-hand side are more metallic in nature than those on the right-hand side. And I mean, you know that we've got metals and nonmetals, but it's because it's so easy to pull electrons off of the larger atoms, which are on the left-hand side. So as you move left to right across the periodic table, metallic nature decreases. Okay. There's one we haven't talked about yet. EA. This is Electron Affinity. Basically, this is the energy released. Oh, can't spell. When an electron is added. By definition, it's the energy released when an electron is added to an atom. Except the problem with this is some elements you actually have to put energy in order to make the atom accept an electron. Like a metal. A metal doesn't want to take one. If you push it in with enough energy, it'll take it, but it won't stay. So this is typically the elements that have high electron affinity are the nonmetals. So they want to add electrons, and it's easier because they have more control. Due to their size. So nonmetals want to add an electron, and it's easier because they have more control over them because they're so small, because their number of protons is so big. So ionization energy, the nonmetals have a high ionization energy. They also have the high electron affinity. So basically nonmetals, low electron affinity, because they do not want you to add an electron. If you form positive ions, so if you lose electrons,
What's the subtitle?
Let's make this one then cations, okay? Positive ions. Cations lose an electron or lose electrons. They lose electrons. Have the same number of protons as their atom. A cation is a positive ion. So cations lose electrons, but they have the same number of protons as their atom. So potassium still has 19 protons. Calcium still has 20. So what happens is protons repel each other because they're the same charge. Electrons repel each other because they've got the same charge. But protons and electrons attract each other. So when you lose electrons, there's less electron-electron repulsion, but there's a greater positive-negative attraction. Okay? So this is just for an atom, just potassium, or just calcium. This isn't comparing the two. So there's less electron repulsion. So the atom gets smaller. The more electrons you have in your outer shell, the bigger you get. So you've lost those electrons, the positive pull is the same, so there's less repulsion, so they start coming smaller. What happens here is the more electrons you lose, the smaller the atom. So calcium has got a bigger pull than potassium, and therefore it shrinks even more. It's not because of the electron-electron repulsion here, because they have the same number of electrons. So K1 plus has the same repulsion as the Ca2 plus. So between ions, the ion with the most protons is smaller. Between ions, the ion with the most protons is smaller, i.e. Ca2 plus is smaller than K1 plus. They have the same number of electrons, so the repulsion is the same. How's that? Better? So titanium there lost 4 electrons. So it's got the same number of electrons as potassium, 1 plus, but it's got more protons, so a bigger pull pulling it in. So the more protons you have, the smaller you get. All right, let's take a look at page 53. What happens when you make a negative ion? Gets bigger. Gets bigger than the atom, for sure. They get bigger as you go down the groups, just like the atoms. Now let's take a look at the number of electrons you're adding. Compare neighboring ones beside each other. You see it more on period 2 than you do with the others. It's more pronounced. What happens?
They get smaller
Which ones get smaller?
from left to right.
From left to right. It still gets smaller. Can you guys think about what you're doing here? Why might N3 minus be bigger than O2 minus, which in turn is bigger than F1 minus? Again, think about electron-electron repulsion and the number of protons. Yovam?
So for nitrogen, it needs three electrons to get a full shell. Oxygen needs 2, and fluorine needs 1.
Yeah.
And because fluorine has the highest amount of protons, it means it's going to have a bigger pull, meaning that's going to be smaller than the rest.
Yeah.
Because it has more.
Okay, so the more protons you have, the bigger the pull on the added electrons. So that's going to serve to make them a bit smaller. What's going to be making them bigger? Why is nitrogen 3 minus? What else is at play here? Nitrogen 3 minus, yeah?
Because it has less protons to assist in pulling the
Electrons in, yeah. So, we've got this electron-electron repulsion too, right? We've got the more electrons that you add with the less number of protons, the bigger you're going to be. The lower, that's an E. The lower the number of protons, the more electrons that are added, the less control over the electrons. So nitrogen and oxygen and fluorine have isoelectronic ions, but nitrogen's really only got how many electrons, how many protons, sorry, how many protons to pull on those electrons? Dan?
7.
Yes, 7, sorry. I've got valence electrons in my head. Yeah, there's 7 protons. Nitrogen's got 7 protons. Oxygen's got 8. And fluorine has 9. I almost called you Ben. That's what got me. Okay, any questions? All right, who's bigger? Aluminum 3+ or phosphorus 3-? Without looking at the chart. Just look at a periodic table, not page 52, 53. Aluminum 3+, phosphorus 3-. Who's bigger? Phosphorus 3-. Aluminum got smaller, phosphorus got bigger, because aluminum lost, phosphorus gained. Who's gonna be bigger? Sulfur 2- or argon? What did I ask? Which one's bigger? Sulfur 2- or argon? Sulfur, less protons, same number of electrons. Good. Who's bigger? Beryllium 2+?
Wait, sulfur is smaller than
That's less protons. Who's bigger? Beryllium 2+? Lithium 1+? Who's bigger? Who thinks lithium? Who thinks beryllium? Okay, for the ion, lithium's gonna be bigger. Still only got 3 protons. Okay, you guys are good at this. Okay, that's it for trends. We're going to label. I don't think I gave you guys these sheets yet. Yeah. Some people wish they had that problem.
Whatever, no, you can do all the work for us. I don't want all
Okay. This sheet is just for reference purposes. Didn't come out that great. And then the back of it has board diagrams for the first 20 elements, just because some of you have forgotten. So that was something that my grade 9s did years ago. What I want you to do is you're going to label the periodic table that I gave you, that's blank. You're going to label it with trends. And you'll see it's already got increase. So what increases in that direction? You're going to be labeling 4 things. Size, electronegativity, ionization energy, and electron affinity. So, electron affinity, electronegativity, ionization energy, and size.
This one's size, this one's size. This
You put more than one on one?
one of them is size. This one is size.
It does work. The electro, the others, I don't know the other colors. I have electronegativity. What size? This is and then affinity. Electric affinity. Oh, how easy it is to plot. I don't know how much energy is really added down. I don't know. Because you told me goes on.
That is size.
That's electronegativity.
Electronegativity.
Yeah.
Right here.
That's a better way.
Size.
Electroaffinity.
Meanwhile, just like
The amount of energy released when you add it. Amount of energy used to release.
If you wrote it down, you would know.
No, it's release. Why does it use?
15 years ago, we were teaching people. And that's for engineering.
Size increases.
When I was, yeah.
Yeah, but anything with these ones, electrons
I
add
went,
one.
actually it's more now. We were in,
That's not size.
Because each shell goes
When you add an electron, these don't add electrons.
So you add an electron, how
So I thought I was
This is exactly what I had before.
I was thinking, so much.
Yeah. Electronegativity.
It's supposed to be so that I was saying.
Electronegativity is how much.
Sorry, everybody. But nobody corrected me, so they just went in. And I'm like, what? What? Where you don't have bad students, you have bad teachers. That I do.
How much energy it takes to work the electron? It doesn't increase.
Yeah, but that's.
Okay, so I'm giving you this periodic table. Hopefully you can label. Yeah. It's gonna be more than one place.
So is this excluding?
No. Switch it with one of your friends. Why did that happen? Seriously.
Is this excluding? What happened?
Okay. What increases going down the periodic table? Size. What increases going to the left of the periodic table?
Electricity goes down.
So, going down, we know size increases. Which other way does size increase? Does it increase going left to right? Or does it decrease left to right? So it decreases left to right, so going right to left, it increases. So on your arrow, going left to right, your size increases. And then the trick for this is, everything else is opposite. So if you increase in size, you decrease electron affinity, ionization energy, and electronegativity. So what increases as you're going to the right is ionization energy. Electronegativity is going to get bigger, and electron affinity is going to get bigger. So going to the right, the other three get bigger. So EN, IE, and EA. Size, that one, size gets bigger than that. What happens as you go up? Are you getting bigger or smaller? Getting smaller, so it's harder to pull off an electron, so ionization energy increases. Electronegativity will increase as you go up. And so will electron affinity. So the size is going to be opposite to the other three. So if your size increases going down, everything else decreases going down. So these two of them. Okay? Okay. You're gonna work on these questions for homework. Okay? Let's get homework. Have a great weekend. I mean, you can make carbon be a carbide. That is a very tough material, but it doesn't want to do it. Share it.
I didn't want to do that before meeting. I didn't want to do that part in the back of that competition. Who's your partner? Jackie. I don't have partner. It's fine. What?
Doesn't he die?
No, he gets like.
You too.
I know.
I'm not here on Tuesday.
Not here on Tuesday.
Do we have anything due Tuesday? Nomenclature.
Nomenclature's gonna be due, so hopefully people will have questions. I'm not collecting it.
Oh, okay.
I'm gonna just give you an assignment on
Thursday.
Thursday.
And then the next Thursday is?
Yeah. Yes, but if I don't give you guys a due date, you guys won't do it.
Yeah.
Well, when I say you guys, I mean in general. In general.
See ya.
See ya, have a good weekend.